Welcome to this video where we're going to look at our second sample statistic and sampling distribution, the sample variance S squared. Suppose we have a population that has a distribution with a population mean mu and a variance of sigma squared. A lot of the inference we've been doing so far has been based on the fact that we know these parameters in the population. But in general, right, these are usually not things that you know. And eventually what we're getting to is we're going to get to a point where we're not really going to know much about the population mean or the population variance whatsoever, and we still want to be able to ask some probabilistic questions and answer those by just looking at a sample and trying to use the sample mean and sample variance to make some inferences on what we think the actual parameter values mu and sigma squared are. So today we're going to start looking at sigma squared and how we can use what we get in the sample variance to get some ideas about what the actual population variance may or may not be. So before we dive in any further, let's just recall a couple ways we can compute the sample variance sigma squared. First, looking at just the original definition we have, 1 over n minus 1 times the sum over all of the values that are the differences of xi observation minus the sample mean x bar squared. That is the sort of original definition. However, in practice, we have an alternative theorem to compute s squared, and I tend to use the following computation: 1 over n times n minus 1 times the quantity n times the sum of the xi squared minus the sum of the xi's. Let's wrap this in parentheses here. Squared. The sum of the observations squared. So the sum of the squares times n minus the square of the sum. And I tend to use the latter in actual computing it, but just want us to recall both of those options as we get started. So the sampling distribution of s squared. Let's dive right into theorem 8.4. It says if s squared is the sample variance, s squared is the sample variance from a random sample of size n, taken from a normal population, with variance sigma squared, then we get something called chi squared is equal to n minus 1 times the sample variance over the assumed population variance. And in terms of actual computation here, this is equivalent to, if you have the sample, the population variance sigma squared in the denominator, this would just be the sum of the xi's minus the x bars squared. As notice, if we multiply, again, s squared right here, if we multiply this by n minus 1, we don't, this first box by n minus 1 here, we don't, we just have the sum of the xi minus x bar squared. This is just a number we're going to compute, all right? And this has what's called a chi squared distribution. With the book and most tables tend to use the letter v, n minus 1, v equals n minus 1 degrees of freedom. Chi squared distribution with n minus 1 degrees of freedom. So what does this chi square distribution look like? I've got a picture that I pulled from online right here. It looks something like this. And these are the degrees of freedom. So it depends the general shape of the curve depends on your sample size, the degrees of freedom, and that's one thing we'll be paying attention to shortly here, okay? But notice as the degrees of freedom goes up, the curve is flattening out, right? K equals 9 is this red curve towards the bottom, and K equals 1 is this yellowish looking curve right here. I'll mention on this picture, this is just a graphic. All of these do sort of have this general shape of coming back down to 1, so, you know, this yellow curve would cap out and peak out and come like this. This green curve would cap out and kind of come back down like this. It's just a graphical image. It looks like it. These don't increase indefinitely. They will generally follow this shape, like the lower ones. All right, so what's going on here? This chi-squared is a value. This is a number here. This is not the PDF, right? This is not the PDF of the chi-square distribution. This is a test statistic, if you will, that we're going to get. Now, the values that we get here follow the chi-square distribution, okay? So what we can do is we can ask questions and say, how likely is it for me to get a chi-square value that's somewhere between, like, you know, 2 to 4? So how likely is it that I get this number that's between 2 and 4? The likelihood of getting that number, that statistic, follows this distribution, and so I'd be looking at this area under the curve, you know, right here, for example, if I had 6 degrees of freedom. Okay, so that's what we're going to be doing. Now you might be asking, well, how do I know what the area under the curve is if I don't have the PDF to integrate? Well, good news is that we have a table for this. And in the back of our textbook, this is table A5 in the book. Gives the area under the curves. Now this is different here. Area to the right gives you an area to the right, not to the left, like the normal table does. This is the area to the right. All right, so it's a little bit goofy, but we can adjust. So what does that mean? I'll show you the table here in a second, but it has a chi-square. The subscript, then, 0.975, for example, would be associated with a chi-square number where 97.5% of the area is to the right of that number. 97.5% of that area is to the right of that number. Is to the right of that number. All right, and so here's what this table looks like here. Here's our chi-square distribution. It is nice that, at least in the book here, we have a nice picture at the top that reminds us that we're getting the area to the right. So you have on the first column, selecting your row is done by choosing V, which is your degrees of freedom. V, which is your degrees of freedom, okay? And then the alpha, the subscript alpha, is telling you the percentage of the area that is to the right. Percentage of the area that is to the right. So, for example, if I were to look at, let's say, what do we have on this picture here? We had K equals 6, which is this purple curve. If I had K equals 6, and I want to find the value that would give me 97.5% area to the right, when K is equal to 6, that would mean we have 6 right here, 6 degrees of freedom, and 97.5 alpha, 0.975, that's 1.237. 1.237. So right at about here, right at about there, 1.237. Under the purple curve to the right, we are going to get all the way here indefinitely. That would be 97.5% probability, right? So in other words, it's saying there's a 97.5% chance that we should be getting a chi-square statistic value that is greater than 1.237. If we had a chi-square value that was less than 1.237, it is quite unlikely. It is quite unlikely, right? In fact, the general idea when working with this is if we calculate a chi-square value and it's between the chi-square values that would give you 97.5% error to the right and 2.5% error to the right, then the assumed value of sigma squared is considered acceptable. Otherwise, it is not. Otherwise, it is not considered acceptable. So this is a very generous thing. You don't reject the proposed value of sigma squared with, much thought, right? It really has to get something that's unlikely, because what's between these two numbers? Between these two numbers is 95% area, right? So with a given degrees of freedom, we are accepting, 95% of the time, we should be accepting the value. So if we get a chi-square statistic that is so far to the extreme, to the left or the right, then we would consider not accepting the given population variance. All of this talk is very nice, but let's put this into action and see what it's actually like with an example. Let's suppose a manufacturer of car batteries guarantees that the batteries will last on average 3 years. Last on average 3 years with standard deviation of 1 year. Standard deviation of 1 year. All right. Well, we want to maybe put this to the test. We take a look at 5 batteries. 5 batteries in a sample have the following lifetimes. Have lifetimes of 1.9, 2.4, 3.0, 3.5, and 4.2 years. 1.9, 2.4, 3.0, 3.5, and 4.2 years. Should we, based on this sample, should we be convinced that the population standard deviation is 1 year? Is in fact 1 year, assuming a normal distribution. Should we be convinced that the population standard deviation is actually 1 year? Well, in order to do this, we need to calculate a chi-square value. So what do we have in this case? Looking at calculating chi-squared, we need to know n minus 1 times sigma squared, times the sample variance over sigma squared. So what are the things that are known here relatively directly? Well, n, we have a sample of 5 batteries. N is 5. Okay. And sigma squared is given its stated claim to be 1. So we're going to assume it is 1. And we'll see how likely it is to get a sample variance that we got. S squared, our sample variance. All right, I'm going to use the formula like I said I usually tend to use, 1 over n times n minus 1. N times the sum of the squares minus the sum of the xi's, quantity squared. All right, so we need to compute some things here. N is 5, so this is 1 over 5 times 4. 5 times, what is the sum of the squared values? Well, that's just going to be 1.9 squared plus 2.4 squared plus 3.0 squared plus 3.5 squared plus 4.2 squared. We add all that together, we should get 48.26. What are the sum of the xi's? Well, that's just adding up 1.9, 2.4, 3.0, 3.5, and plus 4.2, and that is 15. And then we need to square that. And so we just run the rest of this computation through a calculator, and we get a sample variance, if I round this off to a few places, of about 0.815. 0.815. So, our chi-square value, which is n minus 1 times the sample variance over the standard sample population variance. N minus 1 then is 4. S squared is 0.815. And sigma squared is 1. Sigma squared is 1. So this is 4 times 0.815. This is 3.26. 3.26. This is our chi-square value, 3.26. All right. Is this acceptable? Well, this is considered acceptable if it's between the chi-square value of 0.975 and the chi-square value of 0.025. Well, let's take a look. We need to look those values up, and we have to choose the correct degrees of freedom. We have 4 degrees of freedom, n minus 1. We have 4 degrees of freedom. All right, so we go look in the table, and we find the chi-square value 0.975 with 4 degrees of freedom. 4 degrees of freedom, alpha 0.975, that's the 0.484. Okay, and what is the right cutoff? The right cutoff is at 2.5%, 4 degrees of freedom. 4v is equal to 4. Where's the right cutoff? Where's 2.5%? That's the next page. Right here. V equals 4. Alpha equals 0.025. The right cutoff is 11.143. 11.143. So what this means, right, is 95% probability chi-square value that we compute is between 0.484 and 11.143. Between those two numbers, right? Well, look at what we computed. We have 3.26, right? And so since 0.484 is less than 3.26, and this is between 11.143, we accept the population standard deviation, right? We said if the values between these, the assumed value is considered acceptable, okay? It is reasonable to assume sigma squared is equal to 1. So with that, we could not make any suggestions and say the manufacturer is lying. We don't really have good evidence. All right? So it is reasonable to assume that this variance is equal to 1. All right? If we had calculated a chi-square statistic that was outside of these values, right? Let's say we got chi-square equals 12. 12 is outside of this 95% probability, and that is so unlikely to occur, we would assume it is unreasonable that the standard deviation is 1. If we had a value outside, we would think it is unreasonable that the given standard deviation is actually true. In this case, it was. That'll do it for our chi-square statistic here. We will see you in the next video.